Today the conversation is about using the HP prime variable, storing values and variables and solving systems of equations, both linear equations and non-linear equations. The calculator has a set of predefined variables ready for you to store values in them. Among them there are several groups: real values, the uppercase letters A all the way to Z, and theta as well. You need to store a complex number. Then you have Z0, Z1, 2, 3, 4, 5, and 9. You need to store a matrix, sure, M0, M1 all the way to M9. A list, L0, L1, 2, L9. We will be using those ones a lot in this video and in the following videos. Graphics. There are other two groups of variables for setting variables and system variables. There are also other variable names that are forbidden for your proper use. The following variable names are used by apps. Those variables cannot be redefined by your computations or your programs. The app Advanced Graphing uses variables V1, V2, V3, all the way to V0, and that gets in the way of electrical engineering solving for voltages in nodes 1, 2, 3, 4. Normally we call those V1, V2. Well, we'll find out some other way of naming those voltages. The app Solve uses the variables E1, E2, E3, etc. all the way to E0. By the way, the name E is taken. You cannot redefine that. That is the base of natural logarithms. You can use it, but that has a predefined value. Cannot change it. I suggest that you label node voltages if you're solving for them, something like VN1, VN2, VN3, etc. And for the branch currents, IBR1, IBR2, IBR3, etc. Let's have a look at the calculator proper and see what I mean by it. I go into home mode, variables, and check for real variables, and no surprise, I find the ones I mentioned: complex numbers, list values, matrix variables, graphic variables, settings, and system variables, right? So we have a whole bunch of predefined variables, but it doesn't stop there. We can define our own variables. Here are the class variables defined both by the user and by the programs. We have many other names that are being predefined by apps. And now let me evaluate this expression. 3 plus sine 30 degrees divided by 0.2, that is 5.5. Store that where? In variable A. That's how I stored a value already on the screen of the machine into a variable. I check A is indeed 5.5. I can use that as a value. 7 times A, oh, that is 38.5. I can store that in another variable B. Check. Sure. I could even store that in a variable created by myself. Let's do that. Store in what name? A funny name. My new variable. Enter. Do you really want to create a new variable called my new variable? Yes. You see, it has a value of 38.8. Where is it? Right here. Variables, user variables. You see there? My new variable. Enter 38.5. Sure, let's say that now I want to delete one of those variables I have defined. I go to user variables, highlight that, and click the delete key, and now it's gone. Because there are no other user variables, you see that icon disappears. The button is no more. Let's have a numerical example. This is a circuit that appears very often in Electronics 1. It doesn't matter that you're not into electronics. This is just an example of using the calculator. Very often, we want to redraw that circuit like this. We want to obtain the values VB here and RB in terms of VCC, R1, and R2. How? Using these two formulas. That is all. Let's do the computation. Let me define the variable R1 with the value of that resistor, which is 75,000 ohms, 75 kilos. And R2, another big value, that is 37,000 ohms, 37 kilos. Now, how do I compute RB? Well, that was a parallel of R1 and R2. From a previous video, we already have the program RR that puts two resistors in parallel and says, do you really want to create a new variable named RB? Yes, I do. The value is 24,777 ohms. Define the variable VCC, it's a new variable, and then compute VB using the formula VCC multiplied by R2 divided by the sum of R1 and R2. We are ready? That's how we compute that. Let's move on. Let's work on our first system of equations. Let's say we have that very simple circuit where we don't have a clue what is the value of VTH or RTH, but I apply a known current source on the right with a value, let's say, of 3 amps, and I measure that the voltage that appears is 10 volts with a voltmeter, 10 volts. Immediately, I realized that there is going to be a current flowing. Of course, the 3 amps are going to be flowing counterclockwise, and that will produce a voltage drop in RTH. And I can write a KVL equation in that loop that is no other than this. KVL, number 1, it's my first equation, I'm calling that KVL 1, is VTH plus 3 times RTH equals 210 volts. I repeat the experiment, but this time with another current source, with a value of 7 amps, and the voltage that appears now is 27 volts. I measure that with a voltmeter. I can write another KVL equation, which is VThevenin plus 7 times R Thevenin equals to 27. 2 equations, 2 unknowns. Let's use the calculator, the HP prime, to solve for VTH and RTH. I prefer to work in CAS, so it's not in CAS. I click CAS. Sure, I'm in CAS now. I'm ready. KVL1 is defined as a variable that has an equation in it, VTH plus 3 times RTH, that is equal to 10. And KVL2 is VTH plus 7 RTH, that is equal to 27. 2 equations, 2 unknowns. Now, solve the system of equations. You see the curly brackets there, the braces, right? In there, we write the equations that form the system KVL1, KVL2, and in curly brackets also we have the unknowns we want to solve for, VTH and RTH. Answer, store that in a list, a variable L0, and we can extract from L0 the first value and assign that to the variable VTH, and the second value of L0 and assign that in RTH. VTH is negative 275 volts and RTH is 4.25 ohms. And that was that. You want to see where they are? Not here in users. They are in CAS because I'm working in CAS mode. And they're in CAS, all variables. You see KVL, KVL1, KVL2, RTH, and VTH. Those are variables that I have defined during this little computation. Now let's work with a system of nonlinear equations, at least one of them. A very simple circuit it is. It is a source, a voltage source, 5 volts, a 100 ohm resistor, and a real diode. The voltage in the diode is Vx, the current in the circuit is Ix flowing in that direction, of course. We can write a KVL equation for the loop that says Vx is the value of the source 5 minus a drop in the 100 ohm resistor produced by the Ix current. About the diode, I can represent its behavior with the Schottky formula. Ix, the current in the diode, is 2 nanos multiplied by the exponential of the voltage Vx divided by 26 millivolts. 2 equations, 2 unknowns, Vx and Ix, but the second one is nonlinear, it's non-algebraic. No problem. Let's have a look at them graphically, which is standard convention. In there, we see that the first equation is represented by a straight line in black, and the exponential equation at the bottom is represented by the blue characteristic of the diode. The intersection of both of them gives us Vx and Ix, the actual voltage in the diode and the current in the circuit. But we will do that using the calculator instead. Oh, I'm not in CAS mode. Okay, set the calculator to CAS mode. And we write the first equation, KVL, Vx is 5 minus 100 times Ix. Now I write the equation of the diode that I will call diode. That equation, it's a fine name. Ix is 2 nanos multiplied by the exponential of Vx divided by 0.026. 2 equations, 2 unknowns, but the second one, it's an exponential one. Solve the system of equations. Remember, curly brackets, KVL and diode. Those are the equations. And in curly brackets, solve for Vx and Ix. Enter. It's going to say, well, if you want to use some numerical method or the other, I just type enter and keep going, and I get that Vx is 0.44 and Ix is 0.0456 amps. assign that to a list variable, and then I can extract the first value and assign that to the variable Vx. I can extract the second value from the list L0, that is 1, 2, and assign that to the variable 1x. 45.6 milliamps the current, and 0.44 is the voltage in the diode. Nice, eh? Now let's work on an electric circuit systems of equations. It doesn't matter that you're not into electrical engineering. This is only a pretext to write a system of linear equations. The values, instead of giving numbers, I will give them variable names. V as the value of the voltage source, I as the value of the current source, and the resistances in ohms will be A, B, C, D, E. Now remember, E has a predefined value. It is the base of natural logarithms. I'll call that last resistor F. And the nodes, of course, the reference node, the top node, and Vx, the extra node there. I will assume that the current on the top flows from left to right, and on B2, and on C it flows from top to bottom, and on D and on F. It doesn't matter in the end if I get negative values. I know that the current is actually flowing the other way. I write KCL for the top node, and I write KCL for the X node, and now I proceed. The unknowns are V top and Vx. Two equations, two unknowns. Let's assign the values of the resistances to A, 2000 ohms, to B, 1000 ohms, and you realize that I am assigning all the variable values at the same time, just separating them with a semicolon. At the end of all of that, I type enter, and all the assignments happen at the same time. I've defined all the variables A, B, C, D, and F, and given them values. The value of the source Vs is 40 volts. The value of the current source is 30 milliamperes. And I'm ready. Let's write the KCL equation for the top node that has all that shape, voltage of the source minus top voltage divided by the resistance A. And I have to add the current V of the source minus V of the top node divided by the resistance B, and so on and so forth, right? So that is equal to the value of the current source plus the current flowing from the resistor C, which is the top voltage minus that, and the resistor D as well. I have one more KCL equation that is the equation KCL for node X. Two elements, the current that goes in, V top minus Vx over D, and the current that leaves all the way down. Now solve the system of equations. Remember, curly brackets, braces in the old days. And in curly brackets also, I write the names of the unknowns I want to solve for. V top, Vx, assign that to a list variable so that I can extract those values and assign them to the proper variables. V top, that is the first element in L naught, first row, first column. And in Vx, I assign the second element of L naught, first row, second column. So V top is 12.9 volts and Vx is 8.4 volts. Let's compute a current. The current in resistor AIA is Vs minus V top divided by A, that is 13.6 milliamperes. And IF? Oh, that would have been Vx divided by F, right? Error, bad argument, what is that? Well, what happens is that if is a predefined word, if. Let's call that IRF instead. The current in that resistor is 2.14 milliamperes. And that is all, my friends. Thank you very much for watching, and I hope to meet you again in our next video.